Welcome to the Explainer. So, I've got my coffee on my desk, data on the screen, and today we're unraveling a real scientific detective story hidden right beneath our feet. We're looking at a fascinating and honestly kind of alarming 2025 agricultural assessment report out of western Loudoun County, Virginia. You know, when rivers run low or crops are withering in the sun, it's obvious, right? But the true extent of this particular crisis, it's completely invisible. It's buried hundreds of feet underground.
Okay, let's dive right into this. The report doesn't mince words, dropping this massive reality check. Groundwater is no longer a sustainable water supply in Loudoun County. Yikes! While the surface is clearly drying up and hurting crops, the real mystery is happening down below. This silent, invisible shift of a finite resource threatens literally everything: farms, streams, rural businesses, and tens of thousands of folks relying on private wells.
So that brings up a really fascinating question. How do you measure a resource you can't even see? I mean, you can't exactly drop a ruler into the earth. To find out if the water in the well is still flowing like a dream, hydrogeologists actually have to stress the system. They pump water out, and while the stopwatch runs, they measure exactly how the underground levels react and recover. It's a literal race against time to map out the underground water before it's too late.
To understand how we got here, we kind of have to look back at the long-term timeline. Loudoun has definitely weathered historical droughts. Take 1930, for example. Less than 20 inches of rain fell all year. Or 1998, when it was so intensely dry that a rusted old bridge, submerged since the 1950s, suddenly popped up out of Beaver Dam Reservoir. But fast forward to the summer of 2024, and the state issued a D3 extreme drought warning. This wasn't your average dry spell. Ponds that had been steadily spring-fed for decades, like the ones on Covery Court, they literally vanished into dry, cracked earth.
So, the crucial point is, what does this invisible shift actually cost us? Well, it comes down to a staggering number: 235. That is the exact number of replacement wells drilled in Loudoun County since the year 2000 alone. Why? Because the original wells just straight up ran dry. The water table dropped completely below the reach of the pumps, forcing families to spend thousands of dollars to drill brand new, deeper holes just to get basic drinking water. Crazy, right? To figure out why these wells are failing, scientists do something called a pumping test, and here's where the fun's begun. First, they pump the well at a constant rate for up to 72 hours. Second, they meticulously measure the drawdown. And third, they analyze the data. Picture the hydrogeologist with type log paper pinned on the wall, plotting another point as the stopwatch ticks. They are pumping the curve, letting the straight line show them the exact health and capacity of the aquifer hidden below. What they're primarily measuring during this test is drawdown. Basically, drawdown is the lowering of the water level in a well or aquifer due to pumping. You turn on the tap, the pump picks in, and the water inside the casing goes down. Watching that drawdown dropping is the very first clue of exactly how much stress the underground system is taking. If that level doesn't bounce back up when the pump goes off, well, you've got a major sustainability problem on your hands.
Now, as that drawdown happens, it creates something called a cone of depression. It's exactly what it sounds like: a cone-shaped lowering of the groundwater spreading out around the well. Think of it like a giant dimple in the water table. If we pump too hard, this dimple gets wider and much deeper. And the report notes this can cause massive disruptions. A deep cone of depression can actually reverse underground flows, essentially sucking water out of nearby streams and drying up creeks that local wildlife and farmers desperately need.
And this brilliantly illustrates exactly why Loudoun's geology is so vulnerable right now. It's basically a two-part system. Up near the surface, you have the regolith and saprolite. This is weathered rock and dirt that acts like a giant, shallow water-storing sponge. Beneath that is the solid, fractured bedrock. Now, bedrock has almost zero storage capacity. It just holds water in tiny cracks, acting like transmission pipes. The problem? All the real water storage is in that shallow dirt sponge. If a drought dries out the sponge, the deep rock pipes get absolutely no water flowing into them, and boom, your well goes dry.
To measure how well those rock pipes actually work, scientists calculate transmissivity. Simply put, it's a measure of how much water an aquifer can transmit horizontally. Water has to awkwardly squeeze through all these random fractures and joints underground. By looking at the pump test data, you can literally hear the transmissivity singing in the trend, from the first big spike of data all the way to the quiet tail end, showing exactly how easily or how poorly water moves through these underground channels.
When scientists match that late-time slope to the historical data, a pretty alarming trend emerges.
Just look at the numbers from the report showing average well yield, gallons per minute. Comparing 1980 to 2023, there's been an 11% drop in yield from the primary fracture zones. So even with all our modern drilling tech, the main water-bearing zones in the rock are literally giving us less water today than they did 40 years ago. Let that sink in.
Now you might be wondering, well, if we're running out of water, just drill deeper, right? Actually, scratch that. It doesn't work that way. Digging deeper into the bedrock is not some magic fix for dry wells. Over the decades, average well depths in Loudoun shot up from 300 feet to nearly 1,000 feet. But remember our sponge and pipe analogy? Once you drill past that shallow sponge, there is virtually no storage capacity down there. You're just punching holes in dry solid rock, hoping to hit a random crack.
Now, what's really interesting about this next piece of data is how our own neighborhood layouts are accelerating this crisis. The report looked at over 23,000 residential wells, and it turns out 90% of them are within 550 feet of one another. That causes what we call well interference. When houses are clustered that tightly together, your neighbor turning on their sprinklers can literally drop the water level in your well. It's basically a bunch of competing cones of depression fighting over the same tiny cracks of water. Compounding all of this, of course, is the undeniable factor of climate change. 2024 wasn't just a local, dry patch. It was the warmest year on record globally. As Dr. Christine Kirchhoff points out, the storms we get more often now produce huge amounts of rain all at once that the ground just cannot absorb quickly. Higher temps mean massive evaporation, and those violent, heavy rains, they just run right off into the rivers. We're completely missing out on that slow, steady soak we absolutely need to recharge the aquifer.
So what does this all mean? It means devastating, cascading impacts. Whether it's a step test or a slug test running all night, the data models are clear. We're seeing reduced groundwater recharge, streams completely losing their base flow, and a widespread decline in water levels across the entire county. Honestly, from the field notes scribbled to the models that fit, every dot on the chart has a story in it, and right now it's a story of diminished storage capacity and real hardship for the community.
Let's move to and see how this builds into actionable solutions. We need to, metaphorically, turn the well back slow. The coalition behind this report didn't just point out the doom and gloom. They laid out urgent, necessary policy recommendations for 2025 to actually manage this rapidly shrinking finite resource.
Here are the proposed steps. Step 1. Create a comprehensive water resource protection plan so we can finally understand the limits of this aquifer. Step 2. Petition the state to officially designate Loudoun County as a groundwater management area. That brings in some much-needed oversight and regulation on how much water can be pumped out. And Step 3. Enact a coordinated drought emergency plan. We absolutely have to protect local businesses, farmers, and residents before the next big dry spell hits.
The pumping test analysis is complete, the trends are clear, and the data is plotted on the wall. But the ultimate question still remains. If the stopwatch is still running, how much time does our aquifer actually have left? It's completely up to local leaders and the community to act on this science, manage the water table, and protect that vital aquifer glow before it fades for good. Thanks so much for joining me on this explainer, and I will catch you on the next one.